write your messages. So where we will continue from is where we left off. There were three types of questions we were concerned with the topic of digital electronics. We said one of the questions was defining the equation for the system. The second we said was producing a truth table that shows all the possible inputs and the possible outputs of a system. And the last is to actually go about designing the circuit. So I'll go ahead and start sharing my entire screen so that we can get down to business. So this is the document that we're going to be using for our session. So this document also provides you with a complete summary of everything we've done so far. So in last week's lesson, we essentially looked at the different symbols that make up the different types of logic gates. We said that there were three fundamental gates, which consist of the NOT gate, the AND gate, and the OR gate. All other gates are basically components of the three main gates. So for example, the NAND gate is the combination of an AND gate with a NOT gate. The NOR gate is a combination of an OR gate with a NOT gate. The exclusive OR gate, we saw its own entire design as a specific, so it's made up of multiple gates, not just a combination of two. Here, down here, we then have a list of all of the primary gates with their truth tables. So in today's lesson, we're going to focus on designing logic circuits. The best way to understand what we're going to be doing today is you're going to actually see how the electrical components of a computer can be programmed. So if you're, let's say, writing code in Java or in Python or any other programming language, what happens is when you write the code, you write it in a higher level language that resembles English that people can read and understand. The computer can't read and understand that particular language. So that's why you have to compile the code to convert it into its binary file. A binary file is a file that consists of zeros and ones. The zeros and ones are basically on-off signals that will be fed into a transistor that will then form the logic network design of a program. So just to make sure everything I'm saying is making sense, this is the relationship I want you to understand. As a human being, you write code. So the human being has a file where they write code in any programming language. That code is in what we call a higher level language. The reason why we call it a higher level language is very simple. It's because that's what human beings understand. So if I had a scale and the scale was from high to low, programming languages like Java, which are very understandable to human beings, it's a high level programming language. Things like Python and so on. Whereas here on the very lowest scale, machine code is what computers understand. Those are the zeros and ones. So if you remember, last week we designed a toy car and we actually wrote a program for the toy car where we're transmitting a sequence of zeros and ones. Those zeros and ones was a program. We created a program that will cause the car to move from point A to point B. Let me see if I have that particular document. Yes, I do. So if I go back to the top here, this was the program we wrote. We had a starting position here, and then we had a stop position here. So we wrote the code by invoking the instruction numbers. So we said run instruction 1, then 4, then 1, then 3, then 1, then 3, and so on. So this is the actual code we wrote. This is machine code. So you can see here the A, B, C, D are consisting of zeros and ones, on, off type signals to get certain behaviors. So by stringing those instructions in a sequence, we produce a program that the car can run. So in reality, what you are doing when you write Java code is exactly the same thing, but you're writing it in a very high level language. For the computer to actually understand what's going on, you have to compile it. Compilation of the program basically means you take your code written in, let's say, Java or a high level language, you go through a compilation process. The compilation process is basically the transformation of high level language code to low level language. It's just translation. So the compile process it's like a translation. So it translates code into another form. So after the compilation, we get something called a binary file. So this binary file consist of the same instructions, but in electrical sequences of zeros and ones. So these zeros and ones tells us what circuits to turn on and what circuits to turn off. So in essence, when you write a computer program, you can also draw it as a circuit network diagram. So these logic gates that we're looking at here, if we look at, for example, a design like this design here is a program. That's what you need to understand. When we looked at the addition function last week as a final example, this is what we saw. The addition function, where we use the half adder circuit. If you remember, this was the half adder circuit. No, not this one. There it is. So the half adder circuit is a design that helps us add a single digit binary values. So this is a program that does addition. So any code you write, you can ultimately convert it into a logic circuit network. Is that clear to everybody? So people at home, can I get a quick thumbs up? Hold on, let me get into view. If everything is making sense, can we get a quick thumbs up? All right. So we will proceed with taking a look at how we can convert a scenario into some sort of network diagram. So let's carry on. Using the same document, all the way to the end, we have lots of examples for you to practice, and I advise you practice this for your examination. So for example, if you look at this question 9.41, there are two basic questions. What is the equation of this circuit? And design the truth table. So that's part 1 and part 2, A and B. Part C is what we're going to be doing today, which is to be designing circuits. So the question for designing circuits starts from 9.47 all the way to 9.10. So we have about 4 questions, basically. So I'll start with 9.47. So we're going to walk through the sequence and the steps of how to go about addressing issues. So here we have a situation, a scenario. It says an electronic system will only operate if 3 switches, these switches, here it's written PST. It's actually R. This is a typo. So just be aware, this is R. So it says 3 switches R, S, and T are correctly set. An output signal X1, X equals 1 will occur if R and S are both in the on position or if R is in the off position, and if S and T are both in the on position. Design a logic circuit network to represent the above situation. Now, when you take a look at this question, the first thing that should strike you is confusion. If you're confused and you don't know what the question is talking about, that's a good sign. It means you're thinking. You're not supposed to understand it until we actually dive into it a little bit. So what is the scenario actually saying? Remember, at the end of the day, everything that has to do with our circuits is basically on-off at the end of the day. So if you remember our example with regards to the toy car, we just basically had 4 motors and the motors could either be turned on or off. That's the same thing that is happening here. We've been given a scenario. We need to design a circuit that will transmit or enable the flow of electrical signals to certain components and produce certain binary values. That's what we're going to be doing. So the first step, I'm going to label it here, step 1, is we need to understand the scenario. What is actually going on? So let's go back to the question. We'll begin with the first sentence. An electronic system will only operate if 3 switches R, S, and T are correctly set. So what this means is we basically have a system called X. We'll call the system X. X is the name of the system, and this system can have 2 states. The system can be on or it can be off. Just like our motor, it can be on or off. So this system can be in an on state or it can be in an off state. So the on state is when it is equals to 1, it is set. The off state is when it is equal to 0, onset. So another way of saying 1 is set. Another way of saying 0 is onset or reset. Now, going back to the question, it's now telling us that this system X is controlled by the value of 3 switches. What is a switch? On, off. In this case, the switches are R, S, and T. So it means that in order to control this system X, there are 3 switches, R, S, and T. And just like with the X value, it can be 0 or 1, R, S, and T can also be 0 or 1. Now, before we proceed, I'll give you a very simple example. I want you to imagine you have a shop, and that shop has 2 doors. We talked about this last week. So there's door A and there's door B. And then we have an alarm system. In the example, this alarm system is our system X. The alarm can be on or off. If it's on, it means something is wrong. If it's off, it means everything is fine. In order to have this alarm work, we have to design a program that takes in input from 2 sensors. So we can have for the door A, we can have sensor A, and for the door B, we can have a sensor B. Again, those sensors A and B can be on or off. They can be triggered or untriggered. So if we have the sensor measuring whether the door is open or closed, the minute the door opens, the sensor will send a signal to the system. So what we want is we want a program that will take input from A and B and generate an output to take to our alarm system to help give the alarm a brain so that it knows when to turn on and when to turn off given the condition. So the program here is the set of conditions given that we program for. So for example, we can say, in this case, if any door is open, then ring the alarm. If any door is open, then ring alarm. So this is high level language. I've written a program instruction now in English. If any door is open, ring alarm. That's the instruction. The computer doesn't speak English. So in order to convert this into computer language, it needs to look something like this. This is what it will look like. If any door basically means if door A or door B. That's what that first sentence means. If any door means if door A or B. If any door is in the on position, that is set, then alarm should also be set. So 1 means on. Now I know I'm writing English and converting it into another form of English just so that you understand. But in reality, what's simply happening is if we wrote this program, this is what the computer would see. You have inputs A and inputs B. Then the logic we're using here is the OR logic. If door A or door B, then X. So we would use an OR gate. So OR goes here, value for A, value for B, and then we have as an output our system X. So this will produce the result we want. So in reality, this equation is X equals to A or B. So this is the program code that our computer can understand. And this is the network circuit diagram that represents that particular equation. So that program is a very small program. It contains 1 circuit element. That single program will perform the action that we want. If any of the doors is open, alarm would ring. But in this example that we're looking at in this question, it's saying that this system is not controlled by 2 options. It's controlled by 3, R, S, and T. And it's controlled in a very specific way. That's the rest of the sentence. It now says an output signal for X equals 1 will occur. In other words, our system will turn on and begin working just like our alarm. Our system will turn on and begin working if condition 1, if R and S are both in the on position, or condition 2, if R is off and S and T are both in the on position. So when dealing with these kinds of questions, the first thing we want to do is we want to understand the scenario, then derive the conditions. So step 1 here that we're going to be performing in order to design this circuit, step 1 is identify the conditions. What are the conditions? the conditions for when our system will be on. In this case, when x will be equals to 1. That's what we need to identify. In order to identify that, we come back to the question, as it says here, an output signal x equals to 1 will occur if, so here's condition 1, if R and S are both in the on position. So let's represent that. So the statement says the conditions are as follows. R and S are in the on position. So what does this mean? We'll translate that into a form that the computer can more readily understand. It means R equals 1 and S also equals 1. So R and S equals 1, basically. We can simplify that to R and S being equals to 1. So this is our condition 1, our condition A. The reason why we know there's more than one condition is because of this OR, this gigantic OR here. So it says the first reason why X will be equals to 1 is if R and S are both in the on position. Or, so condition 2, if S is in the off position, if R is in the off position and S and T are both in the on position. So let's represent that. So condition 2 says if S, let's just double check. Sorry, if R is in the off position, so this should be R. So if R is off and at the same time S and T are on. So if we translate that, this is what we get. Here R equals 0 and at the same time S equals 1 and at the same time T also equals 1. So we will label this our condition B. So our first condition is condition A, second condition is condition B, and that's it. So we've derived the conditions for when X equals to 1. What do? We move on to step 2. In step 2, we make use of our truth table to reverse engineer the logic we want. Remember last week, the truth table shows all the possible inputs and all the possible outputs of a circuit. Now we're designing a circuit which we don't know what it looks like, but we know how we want it to behave. So we can create a truth table and fill it up with the values we want and then reverse engineer the logic. Allow me to demonstrate. First thing when doing the truth table is I need to identify how many inputs and outputs I have. So for me here in this scenario, my inputs are as follows. The inputs are R, S, and T. And the output is what? X. Very simple. Once I've identified that, I can go ahead designing my truth table. So I'll put them in columns. So R, S, and T. And then I want my final output X. So I'm going to go ahead and fill up all the possible values of R, S, and T, starting from 0, 0, 0, all the way to 1, 1, 1, 1. And I'm just going to be going in sequential order. I'm just going to be incrementing by 1 to give me all the possible combinations of zeros and ones for this system. So I'll start with 0, 0, 0. Then 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So once that's done, I should have in total 8 entries because that's the number of possible ways of combining two a binary value in 3 positions. There are 8 possibilities. So I should have 1, 2, 3, 4, 5, 6, 7, 8. So I've designed the truth table. Now I need to fill it up with the output. So given the logic, take a look up here. The logic has already been given to us. It says X will be equals to 1 under condition A and under condition B. And the first thing about condition A, it says we need to look for a situation where R is equals to 1 and at the same time, S is also equals to 1. So we now come down to this column. We have R here and we have S here. So we're looking for a scenario where R and S are both equals to 1 at the same time. So we can find here R and S are both equals to 1. So both here we have condition A and condition A, which means inside here we should have 1 and 1. Does that make sense to everyone? All right. So we look carefully. Is there any other place we find a match? No. So that means we're done with condition A. We now move on to condition B. So this condition B is saying if A or B, because that's basically what the sentence says. It says if R and S are both set, or this both will equals to X equals 1. So now we're looking for a situation where R is 0 and at the same time S is 1 and at the same time T is also 1. So we're looking for the sequence 0, 1, 1. So here I can see there is a 0, 1, 1. So this is condition B. Is there another one? Oh, sorry, this is 0, 0, 1. So this is wrong. 0, 1, 1. That's here. So this is condition B. Is there another 0, 1, 1? No. So that means in this section, we should have a 1. And then for the rest, our system X should be off. So we put a 0. We're done with all our conditions. So we've now basically developed the truth table that we want. Once this truth table is developed, we can now move on to designing the circuit. Now, this is where things are about to get real. You're going to have to learn something called a Carnot map. So the next 30 minutes or so, we're going to be doing that. The Carnot map is a tool that helps us convert a truth table's data into a logic circuit design. So what does it look like? Step 3 is the K map, the Carnot map. So there are some resources that I'm going to share with you that are going to teach you about this K map, but I'm just going to give you a quick crash course now. The Carnot map is a table that is like a mathematical tool that helps you to simplify circuit design. What do we mean by simplification? You remember in math, back in your high school days, they used to give you these things, simultaneous equations, or they give you quadratic equations and they say simplify it. What was the purpose of that simplification exercise? The purpose of that simplification exercise was to find the most efficient way of performing an operation. You'll see what that means in a couple of minutes. But anytime I design a system, if I have a set of processes, I can look at those processes and I can attempt to simplify it. If I simplify it, I make things faster, I make things easier, and I make things cheaper. So simplification is all about efficiency. So this Carnot map is similar to the quadratic equation methods you use for simplifying mathematical equations. It just helps simplify things. So when we use it, hopefully we will derive the simplest circuit that matches this operation. So how do we use the Carnot map? The Carnot map looks like this. There is first what we call a 2-input Carnot map. That is a Carnot map that has 2 inputs. So what does it look like? There's the A and the B side. So it's basically this is a 2-input Carnot map. So on the Carnot map, you have all the possible values of A, which can be 0, 1, and all the possible values of B, which can also be 0 or 1. And then you take what is in the truth table and you put it inside the Carnot map quadrants, and then you begin to simplify. Here is what a 3-input Carnot map looks like. In a 3-input Carnot map, you might have A and B on one side, and you can have C on the other side. So here you will have 2 digits now. You can have 0, 0, 0, 1, 1, 1, or 1, 0. This sequence is very important. It's part of the Carnot map. It's not 0, 0, 0, 1, 1, 0, 1, 1. No, it's 0, 0, 0, 1, 1, 1, then 1, 0. And then for the C, you can have 0 or 1. So for the 3 input, you simply take the contents of the truth table and you dump it in. Then here's what a 4 input Carnot map looks like. Here you can have A and B on one side and then C and D on the other side. So similar as before, you have 0, 0, 0, 1, 1, 1, 1, 0. And the same thing for this side. 0, 0, 0, 1, 1, 1, 1, 0. Now, it's important to also remember that these zeros and ones represent the values that are attributed to it, A and B in this case. So in other words, this is A, this is B. This is A, this is B, this is A, this is B. And it's just a list of all the possible values of A and B. And here you have all of under this is C and all under this is D. Another thing about the Carnot map is whenever the value is a 0, we put a bar on top of the actual representative. So here it will be C bar, D bar. Here C bar, D. If it's 1, it's just its value. Here is CD and here is CD bar, like so. It's going to be important for us interpreting the circuit. So I hope that makes sense. So in order to demonstrate how we work with this Carnot map, I'm going to shift the 4 input Carnot maps and bring forth the 3 input Carnot map. So I'll shift the 4 and the 2. And we will bring the 3 closer. So this 3 input Carnot map, all we need to do is we need to now transfer all the values that are in it into, let's just shift this to the side. Oops, mutilated it there. All right, so we just need to transfer the values in. In other words, we need to take whatever is in our truth table and dump it into our Carnot map here. So before we do that, we need to label these things. So here we have, of course, A and B, A and B, A and B, and A and B. Wherever we have a 0, we put a bar on top of that particular value. Here we have C, C. Wherever it's a 0, we put C bar. So what we're interested in are all the values that have an on signal, all the ones. So we will start with this first guy here. X is equals to 1 when the values R, S, and T are 0, 1, 1. So I need to find where that is here. Now, on my Carnot map, note that I'm using ABC. I really want to be using RST. So I'm just going to do a quick conversion from ABC to RST. It's the same thing, just different labels, of course. So C will also turn to T. So I will replace that with RS, and this guy will be T. So this guy is RS, 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 and then T, and then T. So now I'm looking for the sequence 0, 1, 1. 0, 1, 1 will occur here. So here I have my RS 0, 1, and my T being 1 is going to be on this row. So that means here I will have a 1. So condition 1 met. Now, for the interest of clarity, I will typically give this a tick to let myself know that I've actually transferred it into the Carnot map so that I don't duplicate or get confused or miss something. The next is this. So I need to do for this scenario where I have R and S equals to 1 and T 0. So I'm looking for 1, 1, 0. And here it is. R and S 1, 1, T 0. So I have another one here. Next, I take a look here. I have the last, so I'll give this a tick. So I have the last, which is just 1, 1, 1. So 1, 1, 1 is down here. So I've successfully transferred everything. Now that I've transferred everything, I want to show you how we can read the Carnot map. We've not finished using it, but I'm going to show you how we can read it. You will notice here that we have 3 1s. So on our Carnot map, there are 3 locations we've identified where X is actually equals to 1. And we can now represent them as circuits. Look at what happens. For this first guy, the mathematical equation for this is RS and T bar. I'll write it. This is its address, RS T bar. This is actually saying if R is true and S is true and T is not true, then X will be equals to 1. RST bar means if R is true, that means R is 1, and at the same time T is 1, and at the same time, sorry, R is 1, S is 1, and at the same time T is 0, then we should have a 1. Now look at the interesting thing here. Look at our statement here. R is 1, S is 1. We don't care about T. T can be 0 or 1. Now let's take a look at the second quadrant, the second one. This guy here is R bar S T. That means R is 0, S is 1, and T is 1. Now look at the interesting thing here. Look at condition B. R is 0, R bar, S is 1, T is 1. Interesting, right? R and S and T, 0, 1, 1. Here also 0, 1, 1. Then for the last one, we read it as R, S, T, which relates to the first one. R is 1, S is 1, T can be 0 or 1. Here, T is 0, here, T is 1. Same thing. You get it? So our conditions, because we said R and S in 1, the other T, if it's 0, we don't care. If it's 1, we don't care. So we take both. So the equation from this Carnot map is actually going to be written as follows. X is going to be equals to this first equation, R and S and T bar, or R and S and T, or R bar S and T. Keep in mind, there's an AND gate in between each of these guys. Does this make sense? So this is the equation of our circuit, and we can now draw our circuit from this. So let's go ahead and do that. In order to draw your circuit, which is step 4, here's what you do. You're going to list out all your inputs. What are your inputs? You have your R, you have your S, and you have your T. Then you decide on which gates, but since you have a hierarchy, you have to be careful of the hierarchy. So the best thing to do here is to put everything in a nice little bracket. So here you can see I have this NOT gate here. So I'm going to put this guy in its own little bracket. Here I have another NOT gate. I'll put this guy in his own little bracket. Then for the rest, I'll put them in a slightly bigger bracket. So this guy, or this guy, or this guy. So using these brackets will help me level all of my inputs. So I'll begin with the innermost things and then work my way out. So I'll start with the white brackets. After I do the white brackets, then I'll do the green bracket. After I do the green bracket, then I'll do the whole thing, which is the red bracket. I hope that makes sense. So starting with the white bracket, which is going to be a NOT gate, I have a NOT gate for T and I have a NOT gate for R. So I'll put on my first column a NOT gate. This one is for R, and another NOT gate. This one is for T. So I finished the white brackets. I can then move to the green brackets. The green bracket says R and S and then T bar. So here I have my T bar. This guy is my T bar. This guy is my R bar. So I can just go ahead and attach an AND gate to make R, S, and T. So I will now have a new column. As I'm building this diagram, I'm creating more columns. Let me move this out of the way. So I'm creating more columns. So I'll now come into another column. So this is my green column. So I know I need an AND gate. So the first AND gate is going to take R, S, and then T bar. Where is R? Remember, this is R bar. I don't want R bar, I just want R. So where do I get R? I get R from this line. This is R coming into the NOT gate. When it comes out of the NOT gate is R bar, right? I want R. So this is R, comes in. Then now I want S. So this is S, comes in. And then this is T bar. So this is T bar. So I take T bar and I bring it in. So this is the first NOT gate. Sorry, the first AND gate. The second green AND gate, I put it below the first one. So this guy just has RST. Remember, this is R. So take this, jump over, jump over. The diagram might be a bit messy, so sympathize with me. So that's R. S is this guy. So I can bring it down here, jump over, in, and then T. Not T bar, so T is down here, like so. So this is RST. Then I can move on to the next one. The next green is R bar. So here's my R bar, right? So I'll again put another AND gate. So I'll pick this guy up. This is R bar. Jump over, jump over, jump over, jump over. So this is R bar. Then S and T. So I can take this S, jump over. So this is S and then T. Take this, jump over. You're supposed to jump over here, like so. Now I deal with the red column, which is an OR gate, and I can have a 3-input OR gate. So this guy, or this guy, or this guy. And at the end, I have my X. So it's a bit convoluted, it's a bit complicated, but we've not actually used our truth table, our Karnaugh map properly. We've simply used the Karnaugh map to translate the answer. This is the raw, unsimplified answer. I'm going to now show you the last step. What I did is we've done the whole thing, but we've not done it very well. In other words, we've solved the problem, but we've not simplified the problem. So now we want to simplify the problem. In other words, we want to go back to the Karnaugh map step 3 and do it correctly and then finish off. Yes? Yes. This is not the Karnaugh map. This one. This is the circuit diagram. This is not the Karnaugh map. Yes, it's necessary. It represents the inputs and the outputs. So let's do the Karnaugh map correctly. In order to do that, I'm going to go ahead and duplicate this. Hold up. I'll just make a quick copy of this. And then we can continue. So this is the real work. This is really what we're supposed to do. So we have these 3 inputs, right? So based on these 3 inputs, we want to start solving our problem. In order to solve our problem, we need to do something called grouping. We need to group these ones into sections so that we can simplify them. So how do we do the grouping? In order to do the grouping, we have to refer to one of the documents that I've already shared with you, which is called Introduction to Karnaugh Maps. So you want to read this document to see everything that I've just explained so far. The actual document we're going to be using for our simplification is this guy, Karnaugh Map Rules for Simplification. So this Karnaugh Map Rules for Simplification document allows us to see the different ways we can form the groupings and thereby simplify our equations. At first, it's going to be a bit confusing, but once we've done it once or twice, it will all start to make sense. So let's begin. There are several rules to grouping. What I want you to understand is, I want you to imagine these ones are students in a classroom. Let's take, for example, you see this class. Do you know how many of you there are? Not present physically in the class, I mean in the whole group. 248. Yes. So in other words, if you take a look at this attendance sheet, you can see there are 380 students in this group, right? That's a lot. Now imagine my life if I had to mark individual assignments. It won't be a fun time. So if I decide to give you an assignment and I say 2 per group, that reduces my work by half. So now I'll be doing maybe 150 or more documents. But what if I struck a brilliant idea and I say, you know what, let's make them 6. So now 380 something divided by 6. Very manageable. So I've simplified my work while at the same time making you better people. You get that idea? So the more people in a group I have in this class, the fewer documents, that's the fewer total number of groups. The more people in the group, the fewer the total number of groups. That's exactly what the Carnot map is trying to also do. You see, in the Carnot map system, all these ones are like students with assignments. We don't want to mark too many. We want to keep things nice and simple. So what are the rules of doing the grouping? Here are the rules for doing the grouping. The first rule says, groups may not include any cell containing a 0. You might have noticed that in our Carnot map, we have some empty spaces. Those aren't really empty spaces, they're zeros. It means we don't care about them. If we cater to the true states, the false states will automatically be taken care of. In other words, if I tell you I'm a guy, I don't need to tell you I'm not a girl. That statement, I'm a guy, is already, it's mutually exclusive. That's what's going on here. So we only care about the ones. So we can have a group of ones. This is right. We cannot have one grouped with a 0. That's wrong. Cannot. Rule number 2. We can group objects vertically or horizontally, but not diagonally. So it means if 2 people are next to each other, we can make a group with them. But we can make a group across diagonally. Either column-wise or row-wise can, no problem. Rule number 3. Groups must contain either 1, 2, 4, 8, or in general, 2 raised to power n members in a group. What does that mean? This is what it means. 2 raised to power n, where n can be 0 all the way to whatever. 2 raised to power 0 is what? In case you don't know, it's 1. 2 raised to power 1 is 2. 2 raised to power 2, 4. 2 raised to power 3, 8. You get the idea? So what we're saying is, I can have a group that is made up of just one person, no problem. I can have a group that is made up of 2 people, no problem. I cannot have a group that is made up of 3 people, cannot. Because 3 is not a factor of 2 or multiple of 2. I can have a group of 4 people, no problem. But I cannot have a group of 5 or 6 or 7 members, cannot. But I can have a group of 8 people. But I cannot have 9, 10, 11 till the next multiple of 2. You get the idea? Very simple. Next rule. So you see here, 2, group of 2, no problem. Group of 3, 3 is not a factor of 2. 4, okay. This has 2 problems. 1, you have 1, 2, 3, 4, 5, 6, 7, 8. While you have 8 people in a group, no problem, but they're containing zeros. So cannot. Moving on. Each group should be as large as possible. This means if I can make a group of 4 people, I shouldn't make 2 groups of 2 people. I repeat, if I can make a group of 4 people, it doesn't make sense for me to split them up and say 2 of you do one group, 2 of you do one group. It's best to have the largest number possible. So if 8 is the largest number possible, we do a group of 8, not 4, 4 or 2, 2, 4 or whatever. We always have the largest. The next says groups may overlap. Now, this in practice we don't actually do, but it means a member can be part of multiple groups, so long as we get a larger group, no problem. That's why you see here, for example, we have a group of 4, and then we have another group of 4 that includes members that appear twice. No problem. That's the overlapping rule. Then here we have another group. It says groups may wrap around the table. This one is a bit tricky. So let me demonstrate. Assuming I have a Carnot map, and let's say it's a 4-input Carnot map. So that means there are 4 columns and there are 4 rows, like this. It means if I'm doing my grouping, if there's a 1 here, and a 1 here, and a 1 here, and a 1 here, how many groups can I have? Technically, this guy is actually neighbors with this guy. It's a sphere. The top is connected to the bottom. And this guy is actually also neighbors with this guy. And the sides are also connected together. So top is connected to bottom, left side is connected to right side. So literally, I can have a single group of 4 members that looks like this. It's a sphere. Now, you may be thinking to yourself, all right, it's all well and fine. It looks simple and straightforward enough, but am I going to be able to remember? With practice, yes, it becomes second nature once you get the rules. Yes. No. So he's asking, very good question. I've never had that question in all my, and it's an intelligent question. He's asking, is this guy neighbors with this guy? No, they are not. Because really, if you fold it up, what you end up having is something like this. When you fold up those corners, this is what you get. So I cannot group this guy like so. I can't do that because I'm breaking the diagonal rule. I can only have vertical and horizontal. I can't have diagonal. So when I switch this into a ball, these areas here, these edges, these 4 edges are represented here. You get it? Well, if you fold it into the 4 edges, that's what you get. So the top left cannot connect with the top right. Cannot. So let's move on. There should be as few groups as possible as long as none of the previous rules are contradicted. So in summary, no zeros are allowed in the group. We cannot diagonal group. Only powers of 2 can be grouped. Group should be as large as possible. Everyone must be in at least one group. That means we can't have a guy not in a group. Even if they're going to be in a group alone, everybody must be in a group. Overlapping is allowed. Wraparound is allowed. And our goal is to have the fewest number of groups possible. Now, with those rules given, we can now come and attempt to apply those rules and see if we can find a solution to our problem. So I'm just going to move this out the way. So down here now, I'm going to start the grouping process. I'll start with the color white. How many groups can I have here? I obviously can have a group of 2 here in the row. In the column. And I can have, maybe I shouldn't have used white. Let me use a different color. So I can have this green group as my first group. And I can have this red group as my second group. So now I've applied all the rules and everybody is in a group. It's a very simple simplification. Yes? That says what? Yes. But the intersect doesn't create a unique group. They just belong. So the question there he's asking is, if you take a look at this guy here, he's part of 2 groups. Does that automatically create a third group? That means we have the green, the red, and then the green intersecting the red. No, that's not how we look at it. As long as you're part of a group, you're good. No problem. It doesn't create another pseudo group. We just have 2 groups. So now to simplify this, we are going to do the same thing we did before. Initially, when we were looking at it in the most simplistic form, we simply took all the individual equations and we did what with them? we added an OR gate to them. So we took this guy and said X is equal to this or this or this. That's what we did here. That's how we got this equation. Very simple. We're going to do the same thing now. But look here, when we use this one single group, we said R and S and T. So if you're in the group, we use an AND. If you're different groups, we connect you with an OR. So that's the same thing we're going to do here now. So that means for the green group, where we have these two members, this guy and this guy, we're going to group them with AND. So that means we're going to say R. You can see there's an R here. Then there's an S. And then there's a T bar. So that's the first one. We will continue. The second one is also another R and another S and T. So this is the green group. So these two ones, their values for RS and T are as follows. And we've connected them with an AND gate. And from here, you can obviously tell if I have R and R, it's still R. True and true is still true. False and false is still false. So R and R is equals to R. T and T is equals to T. S and S also equals to S. But here we have something interesting. We have a T bar and a T. These guys are opposites. It's now a problem. Where you have an opposite, it's basically a conundrum. It cannot exist. So what happens? It dies off. In other words, it's inconsequential. It poofs. It doesn't cancel out. It just poofs. Cannot exist. Cannot coexist. You can't have positive and negative occupying the same space in an AND gate. It's not possible. So what we're left with is the R and R is still R. S and S is still S. So we have RS, RS. We've canceled out the T, which we can then simplify to R and R being R and S being S. So this group now has been reduced to R and S. Then we take a look at the red group. For the red group, you can see the two members again. The first member is R bar S. So R bar and S and T. The second member is R and S and T. So in this case, we have R bar killing off R, and what we're left with is S and T and S and T. And we know S and S is S, T and T is T, so we're left with S and T. So these are the two groups we have. So which means our final equation, X, is going to be equals to R and S or S and T. Does that make sense to everybody? So now that we have the final equation, we can apply that formula we did. We can put this guy in a bracket, 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 and then what? We can evaluate the whole thing. So we will begin with the blue group, and then we will do the red group. So first thing we need to do is we need to list out all the values, all the inputs. So we have R, S, and T. Then we begin with the blue group. So on the first column, we have R and S. So we will have an AND gate, and we will take the value R, and we will take the value S. So this is R and S. Then we take the value S and T, which is also in an AND gate. So we put another AND gate on the same column. We take a connection from S. Notice that we don't do this. It is illegal to draw another line from S like this. We can't do that. Once one line comes out, you just simply connect to that line. You cannot duplicate lines. So S comes in here and T comes in here. I accidentally activated my dictation. There we go. So T goes in here. So this is S and T. And finally, for the green column, it's an OR gate. So it's going to be just two inputs. So here's my OR gate. So I connect R and S and T to give me my final value of X. Now, yes? Yes, can. He's asking if there can be more than two connections in a gate. Yes, it depends on what gate. So what you're seeing now is this. The unsimplified mess is this. What you have here is the unsimplified version. Now, what does that actually mean? I'm going to make a duplicate of it and bring it into view side by side, and then we can compare. So I may need to shrink it a bit. So if you take a look at the simplified version versus the unsimplified version, what do you begin to glean? For the simplified version, we have 1, 2, 3 circuit elements. For the unsimplified, we have 1, 2, 3, 4, 5, 6 circuit elements. We have a lot more wiring, which means in real life, if we were to build these two circuits, they would function exactly the same. They will give us the same results. But the unsimplified version, several things will create problems. One, there are more components to build, which means to build it will be more expensive, bigger, heavier, and more battery consumption because every circuit element needs power. And the time to actually process everything will be slightly longer. The other one is smaller, more efficient, more compact. Now you understand why your iPhones keep getting thinner and thinner. Because they're actually simplifying the circuit design, but drawing out even more power. So you can make things smaller, but to make them more efficient, you make things simpler. So this is why you were taught those quadratic equations and simplification in mathematics and so on. There's a real practical benefit towards operational efficiency. And that concludes what I wanted to teach today. So the best way to actually follow up with this is to practice. And to practice, you already have this document. So there's a question 4, there's a question 9.48, 9.49, and 9.410. I will be providing you with the solutions to the Carnot map so that you can check your answers to see if it's right. But I will not draw the circuit. The circuit drawing should be simple enough. Right? So I'll go ahead and open the floor for any questions if anyone has. So I'll start with the people online. Okay. So here there's just a general conversation. Can I use Boolean algebra instead of this Carnot table? It's called the Carnot map. So they're asking, can I just use a different method? No, you cannot, because the examinations are already standardized, and we have what we call a marking scheme, and the marking scheme is in the form of this Carnot map. It expects you to learn the use of this Carnot map. So unfortunately, in real life, you can use whatever method that gets you the solution. But as far as the university is concerned, in any academic evaluation, you should use the methods that are expected. I am sure of it. You can use the lecture. Sir, do you have a physical class? So this gentleman is asking if I have a physical class. 2 weeks ago, right? We made the announcement 2 weeks ago. If you look up here at your Teams page, a few students mentioned that they would like to have a location on campus where they can attend the lesson. The class is not physical, but we've provided this room B55 and I made this announcement about 2 weeks ago, we've been allocated B55 for you to have a sit down. You can come in and sit down. It's just a space. I'm also present in the space, but it's not like a physical class. We're still conducting everything online. The physical space is just in case people who have lectures after and maybe they're constrained for time, they don't have any place to sit. That's why this space is provided. So even if you come to the class, you're expected to come with your headphones and your laptop so that you can actually see my screen. I'm not drawing anything on the board, and I'm not printing or showing anything that you guys at home are not already seeing. So it's just for convenience. So if you find it convenient, you happen to be in the university, and maybe before you get home, the time will run out, you can just basically pop in, essentially. So where was I? Could we have a break for 10 minutes? So this guy is asking for a break. He has no idea we've even finished the class. I'm just doing Q&A now. We finished what we need to do today. Okay. How can I know which input table I should use? So this guy is asking, Omar is asking, how do I know which input table I should use? He's asking whether I should use the 2 input, the 3 input, or the 4 input. It depends on your input. So here we already know what our inputs are, R, S, and T. There are 3 inputs. If our question was just 2 inputs, we would use 2. If it's 4, we would use 4. It's very simple. The question will tell you what inputs you should have, and then figure out which question did I skip twice? Lecture. What is the answer of Arba and Arba? Yes, Arba and Arba is Arba. So the guy is asking, I didn't notice the question. He's saying if R and R is equals to R, what about Arba and Arba? What is it equals to? It's also equals to Arba. So no brainer there. What about attendance? I'll show the attendance later. When is the exam? I have not set an actual date, but it will be after your resumption. Next week, you are going to be on vacation. I will make the announcement next week as to the time. It will be when you resume next. Because there are 380 of you, we're trying to figure out the best venue, and we don't own the venue. So we have to make a booking. The booking has to be confirmed before we can announce. But you can expect it the week of your return or the week after. So either the week of your return or the week after. We have a class on Monday as you resume, yes. So it could be that Monday after your holiday. Yeah. And this is coming out. What we've done, everything from now till previous, everything is coming out. Is there a finite amount of inputs you can input into a Carnot map table? Not really, because what happens is, it's an interesting question. After, if I have 4 inputs and 4 inputs, where did we draw 4 inputs? Yeah, if we have 4 inputs, what happens if we have 5 inputs? What happens with a 5 input table is very simple. So if you have A, B, C, D, E, then the way we would draw it is you will have 2 tables. So you will have this first one, and you will have this second one. So this first one will be for E, and the second one will be for E bar. And then you will now have to start doing 3-dimensional grouping, because now you have a stack. One thing is on top of another. So if you have one here and one here, these guys can now be part of one group in a 3-dimensional space. So it gets confusing. It turns into a matrix. So we won't give you questions like this because the complexity is just not convenient to deal with on paper, right? But conceptually, you should understand exactly what is going on. So yes, you can have more than that. You can have really infinity if you like, but it will just complicate the tables. Sometime we face trouble in joining the meeting. Why does this happen? This could be due to a number of reasons. It could be the school's network. It could be your network. It could be your computer. It's impossible to say unless the machine is in front of the technical people, and we troubleshoot. So if you continue facing this problem, maybe what you should do is find some time and go to the technical assistance office and explain it to them. They might have a solution for you, or they can help you diagnose it. Why do you finish recording before Q&A? I actually didn't. The recording is still going on. Oh, maybe he's asking for previous classes. Okay, if you want me to record the Q&A, I'll also do it. No problem. Next time. Sir, can you please explain / tell the slides that we're supposed to study? The slides you're supposed to study are everything that has already been uploaded, which is everything we've covered already. So if you go to your file section, under class materials, lecture slides, you have everything, including the logic gates, everything. So 0 to 1, 2, 3. And if we cover an extra topic when you resume, that extra topic also becomes part of the examination. The exam is going to be from wherever we stopped. Could you give attendance? Yes, I'll give attendance at the end of this. May I know how many inputs can a K-map cater to? Like we mentioned, almost infinity. Why not is R? I don't understand. Yusuf, you can clarify your question. Can you tell us what are the topics? I just did that. Can you suggest YouTube channels or series or clips? I want to study more about system software. System software isn't really a topic, it's a group of topics that have been curated. Haven't I shared this channel with you guys, Crash Course Computing? I did, right? So I think there is a sub-channel under your SSC. See, I have a sub-channel called recommended videos. In that recommended video, I've just uploaded one thing. All right, I'll put more videos here. I'll populate this later on. So this is a good reminder. I'll populate that with interesting videos that relate to the subject. Okay, so Yusuf is asking, why is R bar and R bar, where did we write it? He's asking, why is R bar and R bar not equals to R? Thinking that this is mathematics. This is Boolean algebra. Remember, the R bar means opposite. The and is not multiplication. It's an and. The or is not addition. It's an or. You get it? In other words, in Boolean algebra, 0 or 0, which we write as 0 is equals to 0, 0 or 1 is equals to 1, 1 or 0 also equals to 1, but 1 or 1 is also equals to 1, not 1, 0. It's not addition. It's Boolean algebra. So negative and negative does not equals positive. This is not negative. It's the opposite of R. So R bar simply means we don't know what R is. If R is 0, the opposite of 0 is 1. And if R is 1, the opposite of 1 is 0. At the time of solving, we don't know what R is. So R, or the opposite of R, and the opposite of R is still the opposite of R. Because it can be 0 and 0, or it can be 1 and 1. We just don't know. So R bar and R bar is still R bar. And R is still R. That should make sense, right? So we're not doing mathematics here. We're doing Boolean algebra. I don't know who those people are. I just know they play football. I couldn't pick them out of a picture. I'm not a sports person. A student is trying to join. He is new. Okay, for whoever is trying to join, you can just you can share the class code with them. Let me just open up the class code. So this is the code. So you can pass this code to them and ask them to join the team. They'll just click join and then insert the code. Will we be notified at least a few days? You will be notified by next week. Yes, you will have at least a week before the announcement and the test, before the test, after the announcement. We have to study only from slides. I don't generally advise students to study slides because slides are just a summary of what we've covered. You have your recorded sessions. Remember, I'll be correcting last week's recording. You also have a textbook that I've given you. The textbook covers in more detail. You study the textbook, you use the slides as a summary note, and for any concept that is not clear, you jump to the video. Very simple. So you have 3 resources available to you. How long prior will be? At least 1 week. We will give you 1 week notice. Will the exam come from only the slides? I will not ask you what I have not taught you. All the questions will be from the topics we've covered, directly, things that we've dealt with. So there won't be any surprises. The date will be announced next week. Can we combine horizontal and vertical groups into one group, 3 numbers? No, you cannot. So why we delete T bar and T? T bar and T cancels out because logically it's a fallacy. I can't really go into the philosophy at this. You need more prerequisite knowledge for you to understand the proof. In fact, you guys, does anybody here know how to prove 1 + 1 = 2? It's a very complicated equation. There's a proof for it, but you can't do it because you don't have the prerequisite knowledge. But there's a proof for why 1 + 1 actually equals 2. So it's kind of like one of those philosophical situations. T bar and T is not 0. It cancels out. They don't exist. Right? It's not a 0. It cancels out. So this guy has a computer that is charging. Maybe it's the Holy Ghost. I don't know. Yes, for the last week's class that was an error caused it to terminate prematurely. I will be uploading a newer version, so don't worry. Is this textbook available at APU Library? Yes, but I don't know how many copies there are, but you have a soft copy you can download here. So this is already a PDF that you can download and use it in your own home. I've already provided it for you. Okay, this guy is asking for past questions. I'll see if I can gather up something. But for logic gates, these are all questions. This entire document consists of questions, and I'll provide you the answers for this. The others are basically learning questions. You just have to, whatchamacallit, you just have to read and remember information. The only thing that you'll be doing calculation related will be the topic of logic gates, most probably. So so for now, the exam is up until logic gates. After that, we have CPU and memory. And I think that the CPU and memory will also be, if we are able to cover the topic, we will include it in the exam once you resume. So all of that information will be formalized later. So people in the room, any questions? Any questions? Yes. In the what? Can you use calculator? I won't ask you those questions. Binary conversions, I won't ask you. Those are ridiculous questions. They're too simple. I won't ask you that. Why would I ask you that? It's ridiculous. You've done it in math already. You're familiar with it. You know the concept. Why do I need to test you on something you've already been tested on? Nope. What you need to concentrate, the most important thing is this logic gates. It's the most difficult thing you'll probably face. The test is not difficult, by the way. It's not difficult. 4 topics that you've covered, that's it. You're even lucky you have 2 tests, you know. Ordinarily, everything will be lumped in one exam. Now you have 4 topics you finish, then another 4 topics you finish, kalas. And you've seen how easy the assignment is. Very simple. So the guy who wants to collapse, I don't know why he wants to collapse. So in any case, I'll go ahead and stop the recording. I think that's enough for that. So next holiday, after the holiday, I'll make an announcement with regards to the test date. And also the next topic we'll be entering is CPU and memory, where we'll look at the final pieces of the hardware that we'll be covering.